So now we're going to shift a little bit the subject here. We're still talking about data, but in a kind of a different way, okay? So we're going to look at some Six Sigma metrics. So imagine that you collected data about your Y variable, you did all that beautiful stuff and histograms and box whiskers plots and run charts and all that, so still playing around, and we want to look at in a quality perspective, right? So we want to know the quality level, let's say, of a process, and how much defect it's generating. Again, a quality defect doesn't mean an actual defect. It could be something that's outside the limits. Let's say we have data about on-time delivery, and we want to know how many days we were outside that limit, right? We have data about productivity, and we want to know how many days we were below that target level of productivity. So whatever your performance metric is, and whatever you identify as a quality problem in your performance metric means that you're not performing as good as you want it to be, okay? So again, there's two ways of doing things, the continuous way and the discrete way. So if you have a continuous data, we're going to look at first, then discrete. So continuous, we need to understand the expected level of defects, so the percentage of output that's going outside the limits that we're going to consider to be defect, the K-sigma levels, and the DPMO, okay? So we're going to do this experiment in class. We're going to roll some dice, and we're going to see how the distribution look like, right? But thinking about a histogram and you're kind of understanding the distribution of something, right? And we're going to do that with rolling dice, right? So imagine that you have two dice. I should be more prepared, but I'm not having it here. You have two dice. They have six sides, and you throw them, right, many times. How do you expect the distribution to be? So we're going to see in class how the distribution is, but it's all related to probabilities, right? So how many 2s you think you're going to have? How many 12s do you think you're going to have? How many 13s do you think you're going to have? How many 7s? So you think you're going to have the same amount of every number? Do you think some numbers are going to have more, some numbers are going to have less, right? So let's think about a 2 and a 12, which is the kind of the most extreme, right? When do I roll a 2? Well, only when I have 1 and 1. Any other case is not a 2. When do I have a 12? Only if I have a 6 and a 6, right? When do I have, let's say, a 6? Well, I can have a 6 by having a 1 and a 5. I can have a 2 and a 4. I can have a 3 and a 3, right? And also, I can have again a 4 and a 2, or a 5 and a 1. So there's a lot more chances of having a 7 than is having a 2 or a 12. And that's basically because of the odds, right? Because of the probability of these values to happen, right? And if I put in a histogram, and we're going to do this in class, you're going to see that the values in the middle are usually a lot more frequent than the values on the edges. And that's what a distribution, a normal distribution, is, right? It's a distribution that's look like this. So you have a lot more center in the mean and very little. So this is a very beautiful kind of normish distribution. Yours is not going to be that beautiful, but it'll be something similar to this, right? And we're going to have something like this, so you can say, okay, what is the probability of me rolling a 12? You know that, right? You know that the probability of these in the bottom. What is the probability of having more than 11? What is the probability of having more than a 10? Because you know how the distribution is. And that's the same logic that we're going to have for the normal distribution. A normal distribution is a distribution that I already know how much you have, you know, on the right side or on the left side, right? And I know how much do I have after 1 or 2 or 3 standard deviations, right? Because a normal, where is my mouse now? Oh, here it is. A normal distribution is basically a distribution where the mean is 0, and I have 1 as standard deviation. So 1 plus 1 plus 2 plus 3 minus 1 minus 2 minus 3, which is the same thing of having whatever I have and have a mean and have a specific standard deviation, right? And the z-score is going to help us use this standard normal distribution to find out those spaces, right? To find out the probabilities higher than 1 standard deviation, higher than 2 standard deviations, higher than 3 standard deviations. So the z-score table, remember the z-score table? That one that looks like a matrix? I have one here to show. Do you guys remember this? Yeah, you have in your notes. We're going to use that beautiful thing, right? So it looked like the film matrix. We have numbers there and you kind of lost. We're going to decode that again. You guys are going to remember how to use it, and we're going to use it. Okay, so think about that. I have a distribution. I know the distance. They're all in this table, and then whatever I find out, I can compare them to this and find the percentage and find the standard deviations, the distance, and what that distribution look like.